But thanks for joining us. I'm Adam Sled. I'm the Executive Director at Dominion Energy Innovation Center. This is Braden Croy, furiously typing away so that we can get more folks in the room. In the meantime, I would like to thank Brandon Martin and Jerry Warchol for joining us today to talk about battery storage and some of the many awesome projects that Dominion has going on, kind of why they're relevant, what's happening across Virginia, and maybe we'll get into a little project or two kind of more in depth. So this is a hot topic, and it was something we had just thought of the other month or actually maybe 6 months ago. I want to say, Jerry, it was like 6 months ago that I was trying to figure out who I could find to talk about battery storage, because we thought it was just such a cool topic and knew that you guys had a bunch of things going on. And it took us a while to kind of figure it out and get the two of you all set up with slides. But here we are. And so, all right, we've got more people coming in as we go. So that's a good sign. So we'll just get going and dive in. I think, Brandon, you're going to lead us off today. And then Jerry's going to dive in with some more of the details on how these projects are actually working out. If you have questions, feel free to drop them in the chat. So we're doing this webinar style. So just put your questions in the chat and we'll try to, we might get to a few of them kind of while we're going, but we're going to plan to leave some room at the end for Q&A. So hopefully we have a great conversation towards the end of this. But Brandon, you about ready to lead us off?
Yeah, that'd be great. Yeah, thanks so much, all. Definitely appreciate it. My name is Brandon Martin. I manage the business development team focusing on energy storage, reliability, and resiliency. And really what that means is that we're focused on generation here in the Commonwealth of Virginia. So let's go to the next slide. So knowing that a lot of folks, internal to Dominion or external kind of may not know exactly how this filters up, but we report to the Vice President of Business Development, again, Dominion, Virginia. And my team, we do a lot of different things. We focus on, an annual RFP to meet the Virginia Clean Economy Act. We'll talk a little bit more about that. We do where projects are submitted into that RFP by developers. Those are, sites that have the potential for whether it's solar or energy storage. They have, done a significant amount of surveys and permitting work, worked through the interconnection process. And so our team does a lot of the diligence, working with subject matter experts to satisfy the VCA and, hold that annual RFP. And then we also support regulatory filings with State Corporation Commission every single year. But also our team does project development where we take on site control. We do the site evaluations. We work a project through its county and local permitting. And last but not least, our team also does technology evaluations, and we'll get into that a little bit more, but that can be anything from various types of energy storage technologies, how they're progressing in the development and diligence of that technology evaluation. And then I'd be remiss if I didn't mention, we work very, very closely with the risk team evaluating technology safeties and spacing and setback requirements, things of that nature. So I'm a dad and I love dad jokes. So if we can go to the next slide. So we need to invest in solar. It's just not going to happen overnight. And it cracks me up, a little energy humor. And here at Dominion, obviously, we are doing a lot with solar, but there is an intermittency associated with solar that we need solutions such as energy storage to backstop that and make sure we have a reliable grid. So let's go to slide 4. So folks that aren't familiar specifically with what a battery storage system is, most folks are aware of what batteries are, whether it's in your iPhone or in your kid's remote control car. But, when we think through battery storage, it's capable of receiving power from the grid, storing it, and then injecting it back into the grid at another time. Now, what you'll see from this is a kind of a standard lithium 4-hour solution, where there are individual battery cells that are, put together in series, put together to make up a module, and then a series of modules make up a battery pack, and then a series of packs make up a battery system. And that's not it. That's not the only things. There are things like battery management systems that control how you charge, how quickly you charge, to what percentage. All right. I think I may have dropped for a second.
You dropped for just a second. We got you now.
Yeah. Let's go to the next slide, slide 5. So where you look at energy storage, and there's energy storage is obviously not a new technology today in its concept, but how it's applied is rapidly changing. And there's really no one silver bullet of one technology that solves all the different complex use cases and benefits that are associated with a battery system. So, in the event that there are, shorter durations, maybe lower capital costs, but then if you need a longer duration solution, it may be something like what folks are familiar with, a pumped hydro system. And really what is going to be critical is, with a grid as complex as PJM's, is that it's going to take strategic planning, a fair amount of time and resources to make sure that we're putting the correct technologies to solve the correct use cases over a long period of time. All right, let's go to the next one. There you go. Okay, so in its most basic form, for those that are not aware of the Virginia Clean Economy Act, it sets a roadmap for renewable energy, whether that's solar or onshore wind with 16.1 gigawatts, offshore wind, and then obviously I'm gonna spend some time on energy storage. But this roadmap establishes a lot of great renewables, but also, has concerns associated with intermittency. So that's where energy storage comes into play. So let's click over to slide 7. All right, so the energy storage VCEA, again, 2.7 gigawatts of energy storage. The State Corporation Commission set interim targets for us to file projects for. And what you'll see is that there's very much a hockey stick effect where can y'all still hear me? Okay.
Hear you, Brandon.
Yeah, we got
So
you.
there's a hockey stick approach here, where there's evolution of technology that will happen over significant amounts of time. There are expected cost reductions, and then there are opportunities for lessons learned. So as we're deploying energy storage projects, and in the long term, that ramp is very intentional. Now, the State Corporation Commission has established 65% of those energy storage targets to be company owned, and then 35% of them to be power purchase agreements. And power purchase agreements are contracts that we have with third-party owner operators where they supply us the power. On the right-hand side, I just love this chart here. It talks about energy storage holistically. It's not just in the confines of what Brandon does in his day-to-day or what Jerry does in his day-to-day, but it also incorporates the end users where they may be placing energy storage at their home. And it also explains the different markets that it serves and whether it's a transmission served in operation or whether it's distribution. And some of these technologies can play in multiple markets. Where you see most of the energy storage being deployed here at Dominion, kind of the highest megawatt totals are in that grid space. And really the focus in the short term will be energy arbitrage, which means, on the sunniest days where there's, plenty of solar, maybe not so much load, we'll charge those batteries and then shift that energy to later in the day. So, whether it's in the peak evening loads, whatever that may be. So, excuse me. But what's terribly critical, and you can stay on this slide, that's fine, but what's critical with energy storage is its capability to be dispatched when it's needed. So this is just a quick overview of the projects that we have that are currently approved by the State Corporation Commission. We have the Dry Bridge project, which is expected to be coming on this year. We have a Dulles Solar Plus Storage project that is going to be coming on out in a couple of years. And then Shan Storage. And you can see that they vary in different sizes. And then, as I mentioned earlier, we have power purchase agreements with third parties that will play into that mix as well. Let's go to the next slide. All right, so while Virginia is one of the largest energy storage targets in the United States, we are certainly not the only one, and we're not the largest. There are currently 11 other states that are either have or are actively adopting energy storage targets. Most folks think of California. California had a at the time it was a target. But what is just wild is what they've announced in the last year is that over about 20 years, over the next 20 years, they expect to deploy 48,000 megawatts of energy storage, and 4,000 megawatts of that they anticipate being long duration. So utilities across the nation are integrating energy storage technologies into their long-term resource planning to support those needs. And what I thought was very, very interesting and intriguing in this chart here, that is the amount of energy storage, talking about non-hydro, not pumped hydro, that has been deployed. And you see this massive ramp up in the last 3 years, and then where this is projected to go forward. And so on the right-hand side, the top chart is just an amazing amount of megawatts that are anticipated to be added, and then correlated obviously is duration on the bottom chart. So megawatt hours that will be deployed. So a lot of interesting and big things happening in that space. So let's go to the next slide. All right, so Jerry's going to spend a little bit more time on this, but the long story short of the pilot projects that we have to to show right now is the GTSA allows for up to 30 megawatts of pilot projects to be developed and over have to operate for a period of time with very explicit requirements of what they're intended to use and do. So whether that's improving the reliability of the electric transmission distribution system, integration of more renewables, things of that nature. But I won't spend too much time on that one. Let's go to slide 11. So what is amazing to me in energy storage space is Dominion kind of finds itself, and a lot of other utilities find themselves in an uncomfortable space where 90% of the lithium that is to be produced and deployed is it not anticipated to be used for standalone energy storage. It's anticipated to be used for electric vehicles or other uses. So standalone storage is anticipated to only take up about 10% of that space. And so, we are in a situation where we've seen a period of raw material costs for lithium. It was declining. Things, there was a great story on that front. But then we hit a period of volatility post-COVID where supply chain issues were creating a lot of issues. And so we saw this period of volatility in kind of starting in late 2021 and continuing all of through 2022. And then here recently, things have started to kind of settle back down. And with this volatility, with the things such as the IRA, which is the Inflation Reduction Act, there are a number of manufacturing facilities, whether it's for lithium or non-lithium alternatives, that have been announced here in the United States. So it's really exciting to see development and manufacturing making its way here into the United States. All right, so last slide. Where we take the next series of pilot projects. Says, as we were mentioning earlier in today's call, obviously we want to do a significant amount of work to, further energy storage, further advance safer technologies, develop lower cost, longer duration. There's just a lot of players in this space. And what I mean players is it seems like that there's a new energy storage technology announced every week. And some of the technologies that we have been following for a number of years have now changed more, have redesigns, things of that nature. But we are in the process of evaluating non-lithium alternatives and long durations that I think we'll be excited to announce later this year. But where we're piloting more projects that serve and benefit the customers in different ways. So that being said, I'll go ahead and turn it over to Jerry, and we'll go from there.
Hey, thanks, Brandon. Appreciate the tee up. I'm going to go ahead and share screens here. And if Brandon, if you can give me a thumbs up, you can see my full slide deck and hear me good. I'll get going here.
Yes, sir. We're good.
Okay, awesome. Well, thanks everyone. Appreciate Adam Sled and Brandon Croy for setting up this lunch and learn. Brandon and I have been looking forward to this talk for a couple weeks now. My name is Jerry Warchol, and I'm the manager of DER integration and engineering for the company. What that means, DER is distributed energy resources. So I run a team of engineers that they study interconnection of, really any generation source or any battery source that hits a distribution grid. And you can think of that, you really just can't plug, a 20 megawatt solar facility into the distribution grid without having issues. So my engineers study that and they spec out the required upgrades to safely interconnect the DER asset. My team has also been very heavily involved in the first couple of pilot projects that Brandon mentioned earlier in the presentation, specifically BEST 1 and BEST 2. So regarding the agenda for today, we're going to talk specifically about the pilot projects. BEST 1 and BEST 2 construction was overseen by my team, and then the BEST pilot project number 3 was overseen by the generation team. So we'll go into the details on all 3 of those. But first, I'd like to hit home a couple slides of why energy storage is important to utilities. The first thing I'd like to look at is the company's current fuel mixture. And I've been with the company 15 years. You've seen a lot of trajectory shift with fuel mixtures. Over the past 8 or so years, we started seeing a lot of renewable resource activity. And what that means for Dominion Energy is solar and wind. We've also seen, as the globe continues to decarbonize, a drop in coal and oil. And the uptick in renewables, renewable energy is great. However, it gives us some engineering challenges for the system. One of which that Brandon identified is called intermittency. And energy storage solutions are the natural tool to correct most of those problems. Oh, hold on 1 second. Okay, so one thing I'd like to go into a little bit more is I'd like to paint the picture of the grid of the past and the grid of today. And in the grid of the past, there was a very clean line of demarcation between transmission and distribution. We essentially generated electricity on the and directly injected that into the transmission system with large, steam-driven turbine generators. We stepped that power up with a generator step-up transformer and injected it out onto that transmission grid. These are the big lattice towers that you see, driving down the street. And then we stepped that power down and delivered it to our end user customers. Then in about 2015, 2016 timeframe, we started seeing that distributed energy resource activity really hitting the grid. And as a result of that, we start seeing the power go in the opposite direction. This isn't a Dominion problem. This is a DER problem, right? And, the system was really designed for that lateral flow from the bulk electric system to the distribution system. Again, what you're going to see is the company very strategically chose this first round of pilot projects to solve each and every one of these problems. So we'll go into that on the subsequent slides. And then Brandon mentioned intermittency. Here we're looking at the typical output of a 1,000 kW solar array. And on a sunny with cloud mixture day, you can see up to 90% surges in the power output of solar arrays. And remember, one key thing about the power system is our generation has to meet the load. So we have to have dispatchable resources. When it comes to solar, one would argue that they are a little dispatchable. It's getting better, but I can remember the days back in 2016. If I put my system operating hat on, PJM didn't even know how to isolate them. So a lot of work has been happening with trying to figure out how to dispatch these better. But the big component that is going to fix that is coupling them with energy storage systems. Okay, let's talk a little bit more about that dispatchable power and, a little bit more education before we get into the pilot projects. I want to focus in on the equation at the bottom part of the page, right? And what that's saying is if you take a look at the little clouds between PJM and Dominion, all of the power generated inside of the Dominion area, plus the interchange, that's P interchange. Remember, Dominion is tied to all of our adjacent utilities, part of PJM, and we have power that comes into our system or leaves the system to match our load. So that generation and that interchange has to equal the load and the losses. So the load is the summation of all of our factories, all of our consumers that are in our area. And the losses are, what's given off in the form of heat to wheel power down our transmission lines and down our distribution lines. So I have to maintain that simple equation every single day, 365.25 days a year. If I don't do that, my frequency goes off. If my frequency goes off, that turns out to be a blackout, a real bad situation. So a little scale up on the right-hand side, if I got too much generation, my frequency is too high. If I have too much load, I have too much demand, my frequency is too low. So every given moment of every given day, this might be an eye-opener to some of you, all of the power is being dispatched to meet the load. So we hire PJM as our balancing authority, and they sit there and they pulse generators on and off to meet that load profile that you see on the left-hand side. So, a typical summer day, we have an afternoon peak about 5 o'clock, 6 o'clock in the morning. We're at the local minima, and then all of a sudden our load starts screaming in. We will peak out at about 1800, 1900 at night, and then the cycle starts over again for the next day. So, these are natural parts to, couple with batteries. It's not easy to build, 1,000 megawatt station in someone's backyard. However, we can take advantage of that local minimum and charge the batteries and then discharge them during the peak. You're going to see that our Hanover project does just that. And that's a natural fit to a problem of having lack of generation. Okay, so finally, we got a little bit of background why energy storage is important to utilities. We're now going to talk about our pilot projects. So you'll see applications for all of these: primary application, secondary application. So this is best one in New Kent County. This is online as of Q1 2022. It's a Tesla Megapack system. It's 2 megawatts, 4 megawatt hours. So if I take that 4, I divide it by 2, I can inject 2 megawatts for 2 hours. This is a lithium ion nickel manganese cobalt battery at our correctional substation. And its primary application is to fix that reverse flow problem that I showed you. Got a real good slide on that coming up. And the secondary application is providing voltage support. So these batteries, they not only charge and discharge watts, but they can supply VARs for increasing or decreasing voltage on the system. And then a little fun factoid: there's 2,170 cells for each of these 2 containers. This is a pretty dense system, believe it or not, when it comes to lithium ion. The containers themselves are 25 foot by 10 foot. Okay. So a little bit more on the specifics of the energy storage system at correctional substation. You essentially have 2 megapack containers sitting on a concrete pad. This was all built in-house by our substation department with a little bit of help from the vendor. Every single energy storage system will have a bidirectional inverter associated with it, and that inverter takes DC power and inverts it to AC, or takes AC and rectifies it to DC for charging the batteries. So those inverter systems for the Tesla Megapack are equipped inside the container. We leave the inverters with sets of 500 kc mil cable. We come to a metering cabinet, and that metering cabinet is essentially a point where we tap off voltage and current signals for controlling the battery, telling the brains of the battery, the TSC, the Tesla site controller, where it's at, if it's putting out the right set point. We leave the metering cabinet, and then we come to a step-up transformer. The low side of that step-up transformer is 480 volts AC. We step that up to 34,500 volts. We go out through a recloser, and that recloser is a fancy distribution term for a circuit breaker, and then we go out onto the system. This fire panel here and the IR camera are very important for lithium-ion batteries. In the worst case scenario, I think people have seen the press on thermal runaway. The fire panel is the computer systems that are looking at thermal conditions to safely shut down the energy storage system. And then we actually designed in the IR camera as a redundant engineering safeguards feature to make sure that if the controls of this new system that we didn't have any experience with did not work, we had a secondary measure to turn the system off. Okay, so back to reverse flow mitigation, would like to talk a little bit more about that. Simplified one-line diagram that one of my engineers put together to identify the use case here. A great shot, but essentially what we have going down at the correctional substation is there is a 20 megawatt solar plant on one of the circuits out of correctional. Well, we coupled the battery in parallel with that. And the problem that you have is if there's not enough native load on this circuit B to consume the megawatts of the solar facility, you essentially see that backflow happening, up through the substation transformer. Some of you may have heard of this as a duck curve. This problem is present all over our system. Anywhere that we have concentrations of, DER and not enough native load to consume it. I would not say that it's a huge problem as of yet. You definitely do not see the penetration that we've seen in California. But ultimately, what has to happen, Brandon was mentioned that need for dispatchable generation. So, basically what happens is when the solar comes online, this lower graph, the load on the transformer drops down. It actually reverses and goes negative, it starts backflowing back out onto the system. But then as soon as the solar starts coming offline, all of that load comes racing back onto the bulk electric system. So all of the generators that are primarily tied to the bulk electric system, they have to play catch up and make sure that that generation and load is balanced. So the more and more penetration you get, the more prevalent this problem becomes. Energy storage is definitely the solution, and that was shown to be possible with the correctional project. Okay, getting into Hanover, this is best two. Primary application is peak shaving to defer transformer substation upgrades. Remember I said charging at the local minima? We're going to see that with this project. This is also a lithium ion battery, 2 megawatt, 4 megawatt hours. It is in service as of Q3 2022. It's a lot larger of a system, 40-foot by 8-foot containers. There's two of them. And fun factoid, 2,904 cells per container. Going into the specifics of the site construction, we have subtle differences, and these were all intentional to test and understand, what our substation department liked better for construction. You saw a concrete pad for the enclosures at correctional, and we have pier foundations here, this middle photo for Hanover. But one major difference is with the enclosures here down along the bottom, you come up, you hang a right, and the inverters are outside of the enclosures. So these batteries are Powin batteries, but the inverters are EPC inverters. So you essentially leave the enclosures with cabling underground. It's a DC. It gets to the inverters. It gets inverted to AC. Goes out through our standard metering cabinet and step-up transformer. So I already have you guys as experts, and you're seeing the very subtle differences between the two. Energy storage systems are pretty easy to construct, as long as you got good people in Dominion Energy that know construction. So I think we learned a lot as a team. There was a lot of people plugged into this project, but we did get it online, right? So let's talk a little bit more about shifting transformer load and what that's all about. We call this a non-wires alternative solution, right? So what we do is we take a transformer and we put a battery just downstream of it. So this is a distribution transformer that's pulling power off of the bulk electric system. So we are trying to charge that battery during low peak and then discharge during high peak. The bigger battery I put there, I can essentially take all the load off the transformer if I had the real estate to do it. But what this is, we call it a non-wires alternative solution because the way that the power system is planned, we expand the system based on load growth, right? So as factories come online and we get more load out of our substations, essentially this transformer gets up to the point that I either got to split out the transformer, I got to put in a second one, or, I got to split out circuits. Well, a battery energy storage system is a new trick. I can manipulate the load curve and charge off peak, discharge on peak. And essentially what I do is I take load off of the transformer to deliver it to the end user. Are we ready to do this as a company for every single load addition project? It's going to be a couple of years, right? So this technology is improving, and our confidence with it is improving as well. But that was all part of the reason that we did pilot projects under GTSA. Okay, this was a very proud moment for the Grid Solutions engineering team when we had our first peak shaving event during the morning of 11/17. We essentially were forecasting a 28 megawatt peak on the transformer at Hanover substation for that morning, and we made sure that the energy storage system was charged up and ready to go. We forecasted that peak to start to discharge. What we want to do is discharge the entire BESS and essentially remove that top portion of the peak. And this graph demonstrates that the battery started discharging at 6:31 a.m., completely discharged, and demonstrated removing the peak of the transformer. And last but not least, coming to a fast stop here, we are looking at BESS pilot project number 3, a very, very unique project. We were talking about that intermittency of solar. Well, this project has 2 components to it. It has a DC coupled component and it has an AC coupled component. And what that means is if I tie the battery energy storage system directly with the DC solar array, I could provide that smoothing because I can control of that upstream and say, make sure you're always giving me 8 megawatts. And when the clouds come over, we can control that set point and take the power from the battery. So this particular project tested and proved that technique to be accurate, but we also have an AC coupled component here. The sizes of them, so the AC side is 10 megawatts, 40 megawatt hours, and then the DC side is 2 megawatts, 8 megawatt hours. These are operational, went into service for the AC side on December of 2021 and the DC side in May. Again, project construction was overseen by the generation department, but this particular project, this was a retrofit of an existing solar facility. So the generation team went in there after the fact and then equipped it with the energy storage system containers that you see in the photo above. And the solar facility that was retrofitted was Scott Solar. That was an existing 17 megawatt facility. Okay, so we've gotten through the pilot projects. We've talked about why energy storage is important to utilities. At this time, Brandon and I will take any questions you have.
Great, really appreciate it, you guys. We'd like to thank everyone for jumping on today. We have a couple of questions here in the chat, and then folks, please remember you can toss them into the chat, toss them into the QA section. We'll get to them. So the first question from Michael Leons: how much energy is lost during inverting and rectifying?
I would say probably 10%.
Okay.
Yeah, I mean, power electronics nowadays are pretty pretty efficient.
Is that a number you see improving even more in the future?
Possibly. I think that those numbers have improved with the different types of switching technologies that they employ. For those that are curious, the inverters at, typically what you'll see is IGBTs. So that's insulated gate bipolar junction transistor, if I remember from school. But they can hold off a lot of voltage. You're dealing with switching, 1,000 volts DC, sometimes 40, 80 kilohertz, very fast, 80,000 times a second. And typically what they do is they, harness the load between an H bridge, and switch like that. I think that the efficiencies with power electronics are probably pretty saturated. There's been a lot of improvements in the 80s, 90s, early 2000s. I don't know if we'll get up to, 98% efficient or something like that, like a traditional transformer. There'll always be losses.
Great. So another one, probably to you, Jerry, is: are the BESS projects configured for potential capacity increases in the future? I.e., can you add more battery containers in parallel if the real estate permits? And this is from Shalani Pai.
Yeah, so I think that, one thing we've learned is for building BESSes inside of substations, it's pretty hard. There we are limited to substation real estate, as the system is kind of expanded around them. So I think we'll be for the pilot projects at Correctional at Hanover, we'll be pretty limited in terms of expanding within the substation. We'll probably do some techniques moving forward with future projects of going right outside of the substation to allow that flexibility. But the one thing is the shell of the system, so the container would stay. Lithium ion batteries die every time you charge and discharge them. And you can essentially operate them as long as you want. It's just in 10 years, they might only have 50% of your capacity. You could think of that similar to like when you're charging your iPhone. When it's nice and new, you got to charge for 4 or 5 days. But, 3, 4 years later, you're charging that thing maybe even twice a day. So you lose capacity. So what we can do is we can retrofit, and add new cells. Like these cells are plug and play modular, and we can bring it back up to full capacity. So if to answer your question, I don't think we'll be expanding inside the substation, but Brandon, maybe you got something to add to that for outside of the substation.
Yeah, good question. And I think, I can appreciate that this audience may not always know the differences between our teams. So obviously with Jerry working, in the distribution side of things, our team works outside, in NPJM space. So if we wanted to increase a battery and add that, we're going to go through the PJM interconnection process, which is a long one. We'll have to work with the county on getting conditional use permits. So certainly can think through that and do that. And as time goes on and we see, hey, we need more storage at one location versus another, we'll incorporate that into our plans. But it on our side of the house, it is not a quick, let's do it in the next year. It's a process.
Great, really interesting. And to follow on to that, Shalani also had another question about do the battery containers need a temperature controlled environment? How do you reduce that fire risk, and what other possible safety mechanisms do you have embedded in those?
They do. They have HVAC systems associated with them. And a lot of the vendors are a little different how they do cooling. So I would say normal state cooling. If you look at Tesla Megapack, they use an R134A and pumps to circulate that through. Wish energy storage systems didn't need pumps and cooling. I'm an ambient temperature, type engineer, not using pumps and cooling mechanisms. So normal state, you'll see HVAC associated with them to keep them cool or even keep them warm if it's cold. They like to be kind of just right in temperature. But then during emergency conditions, you'll see if there is a thermal runaway event, there's, for our safety standards, we have the same safety standards as Brandon's team does. We work with our corporate risk engineering team to kind of develop our fire protection mitigation standards. We typically see hydrogen detection. We see emergency exhaust ventilation. So if we did have a fire, we would want to get any combustible gases outside of the enclosure to make sure that they can't build up in the enclosure and explode. We will see deflagration vents at the top of the enclosure that essentially are designed to lift up and open up the container so it can't explode. But then you have the Tesla device that has spark plugs in it. So if combustible gas is built up inside of the container, they actually light the combustible gas on fire in a puff, almost like when you're lighting a grill and you get that boom, right? And then that lifts up with a vent out the top too to keep from that explosion. So various different fire detection techniques out there. I will say the majority of energy storage system vendors will not pass our fire protection standards. We have a very high safety culture in Dominion Energy, and we were going to make sure that we don't put anything that's dangerous inside of our substations or outside the substations with our generation department.
And I think that kind of actually starts to clue off of, I think, Dimitri, you asked a question about who are the major suppliers. There's a lot of folks that integrate battery systems, but we collectively, and the credit goes to, project construction, who's not able to be in attendance today, and it goes a lot into corporate risk of doing the analysis, testing here in the United States so that we can trust the results of, those thermal runaway opportunities and how to mitigate, whether, as Jerry was mentioning, how do you, in the event that something were to happen, how do you make sure that we're being as safe as possible? And that drastically reduces the number of vendors that we will deal with because of our concern with keeping everyone safe.
So we have Gary asked about Jerry's time on the USS Elrod. So we'll let you pepper that in throughout sometime, Jerry. But yes, we will make a recording of this available. But kind of to that point, Brandon, as you're talking about kind of the safety standard, does that increase the cost? To Anna's question here, what's the cost of one of these storage systems, and what's the payback period?
Yeah, so we're probably not going to get into the costs of these with this audience. A lot of that is pretty confidential information. There are state corporation commission filings where the information can be looked up and things of that nature, and kind of what the benefit to the customer is. But as we mentioned, by choosing certain vendors over others, it makes the projects, can make them more expensive. But it's certainly a situation where we're confident and comfortable with the vendors that we're choosing that are building them the right way.
So to that point, as you look out into the horizon, to Kinder's question here, have they reaffirmed your commitment to these systems? Is there a bright future for them? More deployments, as we can assume, as anything kind of matures, costs come down. Is there a bright future for energy storage?
Well, I mean, Jerry, you were saying that the system worked, right? It did what it was supposed to do.
Yeah, absolutely. I think pilot projects are absolutely critical to test the theories, test the hypothesis, see how they actually operate. And I think Jerry would agree with me. We cannot do this in a just-in-time manner, meaning it can't be we're learning how to operate, how to maintain, how to kind of live with these batteries on the fly. They need to be deployed in real time. I know Jerry does, but we work across the industry with other utilities to learn, peer review, peer learning from one another. The first phase of pilots, I think, are extraordinarily helpful. I'm really excited about the second phase of pilots because, as we mentioned, it seems like there's a new technology that's announced every day. Not all of those technologies are viable. Not all of them are cost effective. They don't maybe make the best use of the dollar for the use case. And so we really need to do a lot of work to diligence that technology, see what the most promising technologies are and what can be commercialized and deployed. And the answer may not be, hey, let's deploy this in California and it's automatically going to work here in Virginia, whether it's use case or grid reliability, or whether it's the geology. Hey, this one is using some subsurface geology technology that is not present here in the Commonwealth. And so really complex answer, but it's an exciting challenge to work on.
You want to relate this to, it was a Tyler who had asked you. They're also looking at
Right. Yeah. So in the Q&A, we also had a question around, is your guys' focus Virginia, and if you're going to look broader, when can South Carolina expect some of these pilots?
Yeah, so our regulatory structure is a little different than South Carolina. Our regulatory structure, has set aside this pilot opportunity for us to use. So I'm not going to speak too much to South Carolina and what they're doing. Obviously, we've had some conversations with them and are certainly glad to share our operating experiences, through that.
We have another question here from Michael on compared to pumped storage, the kind of capacity factors and storage loss factors. He thinks 40% for pumped hydro. Is that kind of in line with what you guys see? And do batteries present a better option on that?
I probably can't speak all the nuanced details on round trip efficiencies and capacity factors of lithium compared to pump storage. Obviously, both have their pros and cons, right? And pump storage, we love Bath County. It is a fantastic facility, but it's an amazingly difficult build. And a lot of capex to build that, different O&M cost structures, things of that nature. So that's what I was getting to earlier. Is there's no one silver bullet that is the best energy storage technology for every situation. We're going to have to look at a bunch of different technologies and work with them.
Jerry, I think you kind of touched on this one earlier, but this idea of kind of plug and play replacements. What is your kind of designed life cycle for either the container as a whole or maybe individual battery packs within it?
Yeah, so I think, it all depends on how much you use them, right? So based on one charge discharge cycle a day, typically what you see from these vendors is they will warranty capacity out X amount of years and say that you'll be down to, 92% based on one charge or discharge cycle per day, in 4 or 5 years. I think, like the pilot projects, one of Brandon's slides outlined that the requirement for the pilot projects is 5 years. But will we run them 10? Probably. We'll probably run correctional in Hanover till just to see how far they go. And then test different strategies of bringing them back up to capacity. So I think the wire, the interconnecting wire, the cabinets, the metal, the transformers, all that stuff is good for 30, 40 years. I mean, it's I worked in North Anna for a long time. A lot of that stuff in there was still trucking along strong, after multiple years. So anyway, I think once you get the shell of it built out, you can plug and play the modules, to bring them back up to capacity.
Great. A lot of really awesome questions in here. So appreciate you guys taking all of these. Srini has asked, can storage be installed on transmission lines at a higher capacity, or is this more of a distribution side play?
I'll take that. I think right now, my opinion is it's really a distribution thing. I mean, direct injection, it depends on how you're using it. If you just want it there for, capacity addition, but if you're trying to fix thermal overloads or contingencies with it, how we operate on the bulk electric system, kind of hard. We need hundreds of megawatts, when we get into a contingency type situation. And, if you were looking at Hanover and correctional, it would be like, 10 to the minus 3 seconds when I'm draining them, right? So you need large, huge systems to fix contingencies like that. But I think wide area deployment, even larger systems, long duration would work. But you're not seeing a lot of like fixing transmission constraints with energy storage at the moment.
Yeah, and this is where Jerry and I, we'll have a friendly debate. Obviously, as I showed earlier, we've got 2 projects that are on the distribution system. Smaller projects, 20 megawatts and sub. But we also do have, our solar plus storage project that is going to be PJM transmission grid. And, our annual RFP does look at both transmission and distribution connected resources. And so, yes, to Jerry's point, and if you look at the IRP and where we do need energy and capacity. So, it'll be both.
Yeah, I'm trying to pick a final question here. Maybe this one is relatively quick. Michael asked, is it more important to maintain the megawatt amount, like the 2 megawatt capacity, or the duration amount? Is one more important than the other?
I think, if it was my bet, I'd want infinity, right? So, right. And completely controllable. So like,
Right.
I think, the tool fits the mold, but something that is completely adjustable and completely adaptable, is what we need. Long duration energy storage is definitely the way to go, but like that peak power output is all kind of on the use case. Complete flexibility, that's what we want, to mimic.
Okay, so that gives me one more quick question. I'm going to close it out to one, so I really appreciate this. As you guys think about these projects, right, and thinking about how many of these projects you're going to be doing over the next decade, looking at, say, a project that you'll be putting together 8 years from now, 9 years from now, what do you think is going to be most different about a project that you'd be putting together and say 2032 from the stuff you're looking at today? Is it going to be like chemistry? Is it going to be size? Is it going to be price? Is it going to be inverter? What do you think is most likely to change in between now and the next decade?
Yeah, I'll jump in real quickly with probably the non-technical answer, but I think the world will look drastically different in 10 years with respect to technology. I really do. I think the geopolitical side of things, the lithium mining, things of that nature, how it plays into EVs, that is all going to look drastically different. And I think we're going to have a stronger opinion and understanding of widespread deployment of batteries, so that we have just a tremendous amount more of knowledge that is going to be critical to where do we go from here. So I just think technology is it's changing pretty quickly. I think that there's a lot of opportunities in that space. But Jerry, I welcome your thoughts.
For the sake of 102, I think that was a perfect answer.
All right. Well, we appreciate it, you guys. Thank you so much. For anyone who jumped on late or maybe has colleagues and friends that missed it, we will be releasing the webinar recording and sending that out to folks. Thank you to Brandon and Jerry for joining us. And we'll be coming back with more Lunch and Learns in June and July and throughout the rest of the year. So everyone have a great day and thank you.
Thanks, guys.
Thank you.
Appreciate it. Take care.
Bye.